Hi, my name is Sergey, and today I will tell you about our library for machine learning enhanced seismic interpretation. It consists of methods for loading amplitude cubes and labels, training and predicting with neural networks, as well as quality control functions and visualizations. All of this is highly optimized and tested on dozens of actively developing fields. So let's dig in. First and foremost, we must be able to infer information about seismic cubes. They are usually stored in segue format and use a different subset of headers for indexing. We hide all this complexity behind just two parameters, which headers to analyze and which of them to use as indexers. This way we can work with both pre-stack and post-stack geometries. At loading, we opt to take extra time to carefully analyze value distributions and other properties of a cube. This is done only once for each field and stored right next to the data for later loads. Display in the instance shows several important attributes, and we usually use it for quick introspection. For example, we can see the area of a field and its shape. During the model training, we repeatedly show an example of input and desired output data to a neural network. That requires high loading speed, and that is not something Segway provides. We would also like to reduce the disk usage, as some of the fields can take up to 1/4 of a terabyte of space. We have developed two lossless formats for storing seismic data with these goals in mind: loading speed and storage efficiency. They are based on well-known scientific storages HDF5 and BLOSK. Under the hood, we leverage the rigid structure of post-stack data cubes, as well as modern compression. We also have two lossy data storages that contain quantized amplitude values. That allows to drastically reduce memory footprint with little to no loss in information. The conversion process takes just a few minutes and can be run by executing the convert method. In the end, we can see that the size of the optimized storage is 4 times lower than the original one. On each field described by a seismic cube, there are a lot of other entities. Currently, we can work with horizons, which are two-dimensional surfaces, flat faces, folds, and geobodies. We have tons of methods for each of them. For example, for a horizon we can remove spikes, smooth out the remaining values, and interpolate all missing points. In data science, it's crucial to look at your data before doing any fancy modeling. We have dedicated graphs to display slices along the chosen axis. Also, we can show attributes along surfaces, which is essential for facial location. Moreover, we have an interactive viewer for express assessment of a field, as well as fully fledged three-dimensional plot. All these functions are part of our library, so it is convenient to use them for exploration. The main purpose of our library is to develop and release in production machine learning models. We borrow a lot of training and inference methods from our parent library Batchflow. For example, a relatively complex model composed of multiple ResNet-like blocks can be configured with a short dictionary. Another feature allows us to generate data for model training in multiple threads, eliminating the CPU delay. We will tell you more about Batchflow in a separate course. For now, let's look at the template pipeline of model training. We use a very similar one to detect horizons, faces, and folds. The pipeline is a plan of actions to perform, and it is easy to read and understand even for people with no programming background. In the first block, we generate locations of a field to train on, then load seismic data and corresponding segmentation masks, and apply normalizations. In the second block, we use augmentations to increase the dataset size, and finally, we use images and masks to train a model on. This whole process is repeated for a number of iterations until the training is converged. The inference pipeline looks pretty much the same. The only noticeable difference is in the absence of test time augmentations, and we use a model to predict, not to train. Our easy to follow and understand pipelines help us to both research different training approaches and present them in a comprehensible way. While working with huge fields, which are described by 100+ gigabytes of raw amplitudes, we want to be very careful with memory management. To this end, we do most of the processing tasks sequentially and work with data in chunks. On the other hand, we want to compute everything as fast as possible, so we use our GPUs not only for model training, but also for the most demanding computations. Inside our library, there is a separate module with optimized functions that automatically choose an available device to use. For example, geological attributes and metrics are all evaluated on GPU, taking less than a second instead of multiple minutes on CPU. Today you learned about our library for seismic interpretation with machine learning. It can work with multiple seismic formats of cubes and labels, train models on them in a highly optimized way, and control the quality of labeled entities. The library is completely open sourced on GitHub, so you can easily test it on your own data. Feel free to ask any questions regarding the usage of SeismiQB on our page, and we will be glad to help.
Hello, my name is Sarokina Svetlana, and today I'll tell you about applying machine learning to seismic interpretation. After seismic processing, we have a three-dimensional seismic volume which reflects underground formations. The next step is seismic interpretation, where we find exact locations to drill in. One of the crucial steps of field exploration is creating its structural model. It consists of horizontal and vertical reflections, and we use it to make decisions about potential petroleum deposits. We will talk about seismic horizon detection as an example of applying machine learning to seismic interpretation. A seismic horizon is a boundary between two rock layers. It's easy to see them on any seismic data, even for a non-specialist. We use them to outline potential petroleum reservoirs, and they provide essential information about the field. During the exploration stage, seismic experts track a lot of horizons for every region. Any inaccuracy leads to overestimating or underestimating the amount of oil. These mistakes can turn into huge profit losses in either case. Despite the importance of precise horizon detection, it has hardly changed for the past 30 years. In most companies, geological experts manually label every point of a target horizon with aid from articulation software. Programs extend labeled points to their neighboring traces, but they work only where reflections are distantly visible, the noise level is low, and the geology is trivial. In complex areas, which is the most interesting, experts still resort to hand labeling, spending up a month on each field. Our idea of applying machine learning to this task is next. An expert labels a few data slices on a very sparse grid, and a neural network interpolates these labels onto the whole spatial range. Now let's look at the code example. It's a fully-fledged notebook with a whole pipeline of creating a very good horizon from a tiny amount of labels. It follows our standard of presenting results and thoroughly describes our datasets, the model training and inference procedures, and more. We start with the imports. Most things are imported from our SeismiQB library. It's open sourced and can be used by anyone for seismic interpretation tasks. We use it for fast data loading, model training, and evaluation of various seismic labels. We load the dataset with one cube and one horizon. Image in cell number 4 shows the horizon surface from above. The color corresponds to the depth for each field point. In the next cell, we can see the front view of the same horizon. It's distantly visible and clear. This horizon was hand-tracked by an expert. We will cut a very sparse carcass and train a neural network to restore it to the whole area. But before that, we must discuss the method of assessing the quality of surfaces created by either humans or models. Without having a reliable metric, it's practically impossible to track the progress of our neural networks. So, we have developed a quality map. that is computed by comparing each trace's labyrinth to a set of randomly chosen reference points. The greener the better. As this horizon is trivial, the whole map bursts with green. The yellow lines correspond to areas of faults or cube defects. On other horizons, in other fields, the metric can look very different and allows us to make meaningful conclusions about surfaces. Note that the computations are heavily vectorized and computed on GPU. By using OpendTect, we speed up this process by a factor of 20 compared to the regular CPU computations. So, having a metric to evaluate our result, we can move forward. As we previously mentioned, we want to train on a very sparse grid cut from the original horizon. It's created in cell number 6, and here is the top view on it. We can see that it consists of just a few slices of data compared to thousands in the whole field. In real projects, our geology experts level 10 to 20 slices in a matter of an hour. So, it's reasonable to test our model by cutting carcasses like this. We generate data for our models in small patches cut along the carcass and want the model to predict horizon location from a raw seismic image. Here, we can see the distribution of sampled data from a training dataset. The rest of the field, which we can see here, can be used for validation and testing purposes. Next, we define our model architecture. It's a custom-encoded decoder consisting of dozen ResNet blocks with visual attention models, and it is roughly similar to DeepLab architecture. We define a loss function, optimizer, and non-integrated scheduler in the same configuration. Also, there is a microbatch key that allows us to accumulate gradient over small portions of a training batch. It's impossible to train large models without that technique. By modern standards, this is a relatively simple architecture. We got it as the result of research over tens of thousands of configurations. It's easy to iterate over them by changing keys and values in the config. We found that some more sophisticated architectures lead to minor accuracy gains, but we believe applying simplicity, reliability, and ease of interpretation is more valuable.
So in this webinar, I'll be showing how OpendTect Python packages could be used for easy access to the OpendTect software and database, which enables access to the project database or survey database. So this allows for easier interactions. This Python tools allows for easier interaction with the OpendTect software and database. And also these Python tools are agnostic to the operating system, so they allow for easier programming generally in Python. And also by using the OpendTect Python packages, you have access to the all OpendTect Python tools that have been developed inside of Python to enable for easier programming from inside of an OpendTect environment. So essentially, I'll be looking at, I'll be detailing how two of these packages could be used in this webinar. The first is the odpy package, which contains some generic tools for working with OpendTect in Python. Essentially, three different modules will be used in this package. The odpy.common, which enables for easier interaction with the OpendTect software and OpendTect software and database. And also the odpy.seisman module will be used, which is used for accessing the seismic database for a particular survey or project. And also the horizon man, which will be used for working with the horizon data needed for this webinar notebook. And the other module is the wmodpy, which is a module which comes installed when you install the WM plugins from the OpendTect installer. So it is used for OpendTect survey and well to access OpendTect survey and well information, and it is a direct binding to the OpendTect C++ code. So it could be more information on that could be accessed from this reference link on how to use it, on how to use the module and get it properly installed for use. And the last module, SeismiQB, which will be used by Sergey, is a Python framework by GazProm Neft, which is used for research and deployment of deep learning models on post-stack seismic data. So that can also be accessed from this GitHub repository. Now to my code demonstration. So originally this notebook, the aim of this notebook originally is to provide a machine learning approach to semi-automatic horizon detection, whereby the user interprets just a very sparse grid of horizon, and then by using the neural network, the whole horizon picking could be done through interpolation with the neural network. So this notebook shows how to do it in details. So I have made some modifications to show how this could be done much easier from inside of an OpendTect environment. So moving on, we have basic importation. Like I mentioned, the odpy common is imported, which allows for basic interaction with the OpendTect software and database. And these are also importations of the SeismiQB, which is used for the machine learning aspects of this notebook. And over here we have global parameters, some global parameters defined for the machine learning aspect as well, the crop shape and the patch size for training and for prediction as well. Now the odpy.common is used to get the data root, which is the survey route to the data folder, and also we derive the survey name, the current survey which we'll be working from, by using odcommon.get odhags. So these two variables, the data root and the survey name, they used later on in the notebook. Then the the train horizon and test horizon names were defined, and also the seismic cube name was defined. So from there, odpy seisman was used to get the file location to the seismic data from inside of OpendTect. So odpy odseisman.get file location returns the path to the full seismic data, which was later used by the seismic data sets from SeismiQB for the creation of the data set objects to be used for training the machine learning model. Then after that, some little demonstration was done to show how odseisman could be used to convert a sequoia data into a numpy array for easier working in a Jupyter notebook. So this seismic contains the convert sequoia to numpy method, which takes in the full part of the seismic data, and it converts a sequoia data into a numpy object. So the convert sequoia to numpy was built on the sequoia IO library. Then once that is done, a little visualization was done here by making use of odseisman.showline. So the odseisman.showline is a method that allows for the display of either an inline, a crossline, or a depth or time slice. So it takes in the data, it takes in the numpy array, which is the data, the seismic data, 3D seismic data. It takes in the ranges, the original ranges of the survey defined according to the keys, the depth or time, the crossline, and also the inline. And also it also takes in the figure size, that is the figure size desired by the user to display the inline, crossline, or depth slice. So once those arguments are passed and the parameters given, you could display the inline, crossline, or depth range easily by using the showline method. So that was also done for an inline here. Then just after that, the wmodpy model was used basically mainly for the access to the horizon data from inside of the OpendTect survey. So over here, od exec platform directory was used, which returns the full path to the release folder of the OpendTect software. So this is required by wmodpy for proper installation, for proper importation, because you need to add this particular parts to the system parts to get odpy on wmodpy to import. So once that had been done, wmodpy was used to create a survey object, and a survey object is created by making use of the OpendTect survey data root, which was gotten initially at the top of the notebook, and also the survey name, which this current survey name. So these two variables are required to create a survey object using wmodpy. Once the survey object has been created, then a 3D horizon object could also be created from it. So this gives access to all the horizon data present in the survey. And as we can see here, we can see all the horizon data, the horizon names from inside of that particular survey. And also more information on all the horizon data present, of horizon data, the depth ranges, the inline range and the crossline range, just by calling the info method from the created 3D horizon data. So once that had been done, the horizon data was also the train horizon data was gotten by making use of the getC method, which was called out of the horizon object created earlier, and could check the shape of that horizon data, and also more information on that particular horizon data. Then after that, odpy.horizonMan was used in the creation of a temporary horizon data. So an horizon file is needed by the seismic datasets class, which will be used for training the neural network. Then for the creation of the horizon data, that was done by making use of create horizon file from odhorizonMan, and it takes in the carcass data array, which was gotten earlier, and also the inline range and the crossline range of that particular train horizon, which was for the carcass. So that was gotten by calling out the info method from the created horizon object, and the necessary keys for the inline and the crossline start and end positions. So with those three arguments, those three parameters, the horizon the horizon file was created, and it returns the horizon file name, which is needed by the seismic dataset to create the trained datasets required by the SeismiQB framework. So basically from here, this concludes my parts of the webinar, and I would hand over to Sergey to show how SeismiQB framework could be used to train and also to make prediction, basically to automate horizon picking using the SeismiQB framework.
In cell number 10, we declare the plan of actions to be performed on each training iteration. First, we load seismic images and segmentation masks, normalize them, apply augmentations, and update model weights in the last action. Running the training pipeline, takes a few minutes and the loss curve shows steady convergence. Despite it, we trained the model for a touch longer, so batch normalization averages also converge. To increase device utilization, we generate data in a separate CPU process. At the same time, our model is trained on GPU, which is a native functionality of our pipeline class and controlled by prefetch parameter. It reduces the training time by up to 2 times. We also use automated mixed precision and it speeds up training by another 17%. We have tested our models on different devices, and here you can see a comparison of a consumer-grade GPU and the DGX A100. The enterprise-grade GPU provides a massive speedup and relieves memory constraints, allowing us to focus on model development. And out-of-the-box DGX achieves this result with no optimizations. A trained model can be used on individual patches of the test dataset, and we can see that model predictions look very good. Probably they are more cohesive than the ground truth. Predictions on small patches are not that useful, and our goal is to predict the whole spatial range. To this end, we split the cube into crops, predict each of them, stitch them into one 3D volume, and extract the horizon surface. It takes just a few lines of code to obtain labeling for 99+% of the cube area. Our metric tells that the predicted horizon is excellent and better than the original one. For example, it better tracks the cube edges. On the other hand, some of the traces are not labeled, and while it can be fine in some places, it's crucial to have a method to eliminate all the holes in the resultant surface. Before doing that, we can compare prediction directly to the ground truth, and we see that they are very much alike. The only noticeable difference in labeling is on the left upper edge of the seismic data, which is expected. We have trained a model to locate a particular horizon on raw seismic data by now. We used labels along with a sparse carcass as a training dataset and have been able to predict the same surface almost everywhere on the cube. To eliminate holes and other minor flaws, we use an additional neural network as a post-processing step. It takes a raw seismic data and a part of the predicted mask and restores the original one. The data generation process, 2 input images instead of 1, is the main difference between the new extension model and the one which we just looked at in the notebook. Also, the extension model has a different output design. We use a softmax activation instead of a sigmoid. This function allows our network to predict horizon on every trace. Adding the extension model at the end of the horizon detection procedure makes the predicted horizons pretty much perfect. There is more to seismic interpretation than just seismic horizons. Along with horizontal reflections, we need to track vertical ones. Notably, the most significant difference to the horizon detection procedure is the data generation process. Once again, by changing segmentation masks, we train a new neural network to predict faults and discontinuities. After creating a structural model of a field, the next step is locating petroleum reservoirs. One more neural network applied along horizons does so. Notice, the main difference is the data generation process. A set of our models allows us to cover the massive part of the exploration pipeline. We have successfully tested the whole procedure on more than 20 fields with varying geology. On the last of our projects, we created a fully fledged structural model of a new region in hours, a massive speedup compared to the months or even years taken by a team of geologists. Our neural networks label every voxel of a seismic field, making a massive step towards eliminating uncertainty in petroleum production. Thank you for watching. You can find more information in the links to this video.